Hello, everyone. Today I'm excited to introduce you to the Spacetime Folding Explorer, which is an interactive educational app designed to make some cutting-edge theoretical physics accessible to people like students and enthusiasts alike. This application explores the revolutionary concepts from my paper on spacetime folding via MEQ geometry and fractal harmonic curvature fields. So whether you're a physics student, an educator, or simply just curious about, the frontiers of space-time manipulation theory, this app provides an engaging way to understand these complex concepts through interactive visualizations and structured learning modules. Let me walk you through what it offers. As you can see, the app features a clean, intuitive interface with a gradient header featuring the blending of space-time dimensions. The app is organized into progressive learning modules, each exploring different aspects of space-time folding theory. At its core, this app tackles one of the most fascinating questions in theoretical physics. Could we potentially manipulate the fabric of space-time to enable technologies once considered science fiction, like faster-than-light travel or instantaneous communication across vast distances? Before we dive into specific modules, let me show you one of the app's most engaging features. It's the interactive simulation. I'll tap this Launch Interactive Simulation button to open our fractal harmonic visualization. This simulation represents how fractal harmonic curvature fields might theoretically propagate through and affect spacetime. Notice the concentric patterns. They visualize the self-similar recursive nature of fractal geometry at different scales, which is a key concept in MEQ theory. And the pulsing effect represents the harmonic resonance within the fields. This visualization helps us intuitively grasp how these abstract mathematical concepts might manifest in physical reality. So Module 1. The foundations of spacetime. So we'll explore this module, and I'll just expand it by tapping on it. This module introduces a fundamental concept in spacetime as a four-dimensional continuum, combining the three spatial dimensions with one temporal dimension. It's essential to understand this foundation before exploring how spacetime might be manipulated. I'll open the four-dimensional continuum submodel. Here we can see an explanation of how space and time are unified in modern physics, along with the mathematical representation of the spacetime interval from Einstein's relativity. In the second submodule, curvature and gravity, this visualizes how mass curves spacetime, creating the effect we experience as gravity. This concept is crucial because spacetime folding essentially involves creating controlled extreme curvature. Moving to our second module, McGinty equation geometry. We explore the new theoretical framework at the heart of this approach to spacetime manipulation. In the MEQ fundamentals submodule, we see the McGinty equation itself, which is psi xt equals psi qft xt plus psi fractal xt dm qs. This equation combines standard quantum field theory with a term that incorporates fractal geometry, which bridges quantum physics with gravity. The quantum foam stabilization network submodule explains how MEQ principles can be applied to create stable wormholes or spacetime folds. The visualization here represents quantum foam, which is the microscopic fluctuations in space-time being stabilized into a traversal configuration through the quantum coherence and entanglement. So Module 3 is localized dimensional contraction. This is the theoretical mechanism for actually folding space-time using fractal harmonic curvature fields. In the fractal curvature modulation submodel, we learn how spacetime's fractal properties could be manipulated at specific locations to alter its geometry. And the key insight here is that spacetime may have a recursive structure that repeats at increasingly finer resolutions. In the harmonic curvature fields submodule, it explores how principles from wave harmonics are applied to spacetime curvature. The visualization shows waves with frequencies that are the integer multiples of a fundamental frequency. So this is creates stable patterns through a constructive interference, which is a principle that is crucial for maintaining stable spacetime folds. And then module 4 is the applications. While these are speculative, these applications illustrate the potential impact of this research. The hyperjump propulsion submodule compares MEQ-based spacetime folding with conventional propulsion systems and other FTL theories like the Alcubierre drive. The key advantage of the MEQ approach is potentially avoiding the need for exotic matter with negative energy density. The entangled data channels discusses how spacetime folding could enhance quantum entanglement-based communication, which enables faster-than-light information transfer. And the time dilation shields explores the theoretical possibility of creating regions with altered time flow relative to the surrounding universe, though this does raise some complex questions about causality and paradoxes. But what makes this app, particularly valuable is for education is how it breaks down extremely complex theoretical physics into digestible, visual, engaging content. It presents cutting-edge concepts from my paper in a way that builds progressively from the fundamental principles to advanced apps. So for students, it offers a structured pathway through very difficult concepts. And for educators, it provides visualizations of abstract ideas that are challenging to represent in any traditional teaching materials. And for just curious minds, it offers a glimpse into the fascinating frontier where theoretical physics approaches what once seemed like science fiction. So the Spacetime Folding Explorer doesn't just teach physics, it really inspires wonder about the fundamental nature of our universe and humanity's potential to understand and perhaps someday manipulate it in very profound ways. So thank you for joining me in this demonstration. I'll be happy to answer any questions about the app or the theoretical concepts it explores.